So did you think about the question I asked at the end of the last video? What should you bet? Because at the beginning of the game craps, when you throw the dice, generally one of the first bets is that you're either going to get a 7 or not. And you can bet for the 7 or against it. So what's the smart bet? Should you bet that you're going to get a 7 or that you're not going to get a 7? And most people think, oh, you should bet that you're going to get a 7 because they know there's more ways to get a 7 than anything. But there are 6 ways to get a 7. That means there's 30 ways to not get a 7. So the smart bet is actually to bet that it's not going to be a 7. See the things you learn in probability. Let's look at a roulette wheel. This is one of those where it's got all these numbers and they spin it and then they throw this little white ball in there and it bounces around as this is spinning and eventually it settles in one of the slots. And when the wheel stops spinning, you look to see which slot the ball is in. And these are numbered and they also have colors. So you have 38 slots, and it is important that you know that that is the total. There's different kinds of roulette wheels. There's American and European. I forget which one this one is, but we're going to deal with 38 slots. You have a 0 that's green, a 0, that's also green, and then you have the numbers 1 through 36. So you have even numbers and odd numbers, and you also have red and black numbers. Now, it's a random assortment of red and black to the numbers. So with the red numbers, there's odd ones and there's even ones. With the black, there's even and then there's odd included within the black, okay? So what we have, you need to know the layout, is you have, if you have 36 numbers, and they don't consider 0 and 00 to be numbers in this case. If you have 36 of them, then that means you have 18 that are odd, you have 18 that are even, and you have 2 that are neither. Even though 0 is technically even, in the world of gambling, it is not, okay? So that would be your 38 slots. If you wanted to talk red and black, 18 red, 18 black, 2 green. So this right here is the layout for roulette wheel, and that should get you through most of your homework, okay? So you need to know kind of that layout, because they'll ask questions about either an individual number or even an odd or color. And the reason why those zeros are there are simply because the casino does not want any odds of any games to be 50-50. They need to skew it in favor of the house, in favor of the casino. So you'll never have a game that's truly 50-50. It'll always slightly favor the casino. All right, so you're going to bet that the number is odd. So I want to know, what's the probability you win? Well, the chance of winning is the number of odd slots over the total. So there are 18 odd out of the 38 slots on the wheel. Let's see, 18 out of 38, if we reduce it, is 9/19. I'm not going to go to a decimal, I'm just going to make it 9/19. Well, actually, no, I am going to make it a decimal. 0.4737. Do you see what I mean by it's not 50%? Even though even and odd, you think, oh, it's 50-50. No, you have a 47% chance. See, they shifted it just off 50-50, and that's how the casinos make billions of dollars every year. Now, what's the probability of losing? Well, if winning means you get an odd number and there's 18 odd, then losing would mean that it was either even or neither. It would be the other 20 slots out of the 38. And that's going to reduce to 10/19. Let's see what 10/19 is. You can reduce it on your own calculator. 5263. So there's a 47% chance, roughly, that you're going to win, and about a 52-53% chance that you're going to lose. I just think it's important that you know it's not actually 50-50, but most people are fooled into thinking that it's 50-50 because they go, oh, red, black, 50-50. No, that's what the green slots were for, okay? All right, let's look at an example with genetics. If you've ever taken a biology class and done a Punnett square, then we're going to talk about eye color in a Punnett square. So it requires very minimal biology knowledge, okay? Let's assume both parents have the brown-blue pair of eye color genes. Okay, so when you're born, You get an eye color gene from your mom, you get an eye color gene from your dad, and the combination of those create your eye color. And we know that brown eyes are dominant. So brown is listed with a capital B because it's dominant, and blue is listed with a lowercase b because it's recessive, okay? If you have big B at all in your little combination, you will have brown eyes. The only way you can get blue eyes, because it's recessive, is that mom gave you blue and dad gave you blue. They have to match to have blue eyes. But we're going to assume, let's say that this is mom and this over here is dad. Okay? Mom has brown eyes. This does not mean she has a brown eye and a blue eye. Okay? That combination gave her brown eyes because she's got that dominant. But she carries that recessive gene. Over here, dad's the same way. He has brown eyes. So let's go through it like a table. So if mom gives brown and dad gives brown, the kid will have brown eyes and will only ever be able to pass on brown eyes. If mom gives brown and dad gives blue, the kid will still have brown eyes, but able to pass on blue to their children. If mom gives blue and dad gives brown, again, the kid will have brown eyes, but if both parents give blue, the kid will have blue eyes. This is how two brown-eyed people can have a blue-eyed baby. It was not the mailman or the milkman or whatever people thought way back before they understood genetics, okay? It's possible. So what is the probability that a child will have blue eyes? Well, there are 4 little genetic outcomes here. There's 4 of them. See the different outcomes? The probability of having blue eyes, there's only 1 square out of the 4 where it's blue. The other 3 will be brown, and I'm not even going to bother converting those because we know that's 25% and 75%. Brown eyes are definitely dominant over blue eyes, and you can see it's like you're 3 times as likely. That's assuming that your parents had this setup, okay? That would be the probabilities. Now, if the setup changes, then the probabilities would change. All right, last thing, let's see if we can set up a tree diagram, because sometimes it's helpful to create the sample space by using a tree diagram if it's complicated. Now, if it's just one die, it's not hard to come up with a sample space, or if it's one coin, it's not hard to come up with a sample space. But what if we want to flip a coin 2 times? So I'm going to flip it, and then I'm going to flip it again, right? And I want to see what are all the possible outcomes that I could have if I flip a coin twice. So we're going to start like this with our tree diagram. Kind of ignore the second branch here. Let me get a sticky note. I'm going to cover up that second branch. Should have had my sticky note ready. Okay. So when you first flip the coin, this is the first coin, this is coin flip number 1, you have 2 outcomes. It could be heads or tails. It's not going to land on the side, okay? It's going to be either heads or tails. Now, the next time you flip the coin, it's independent, or it's what we call memoryless. It doesn't have a memory. So it's not going to remember that this was heads, and then that's going to affect the next coin flip. When you pick that coin up to flip it, it has no memory of what happened previously. So it could be heads or tails, again, on the second coin flip. So if it was heads on the first coin flip, the second coin flip doesn't care. It could still be heads or tails. Or if you got tails on the first coin flip, the second coin flip doesn't care. It could still be heads or tails. So you see how it branches off? And then we're going to read through the branches of the tree. We get HH. So one outcome is heads on both. Or you could get heads on the first, tails on the second. Or you could get tails, heads. These 2 are different because, see, it looks different. And then you have tail, tail. Okay, so your sample space is 2 heads, head, tail, tail, head, tail, tail. Okay, this right here is your sample space of outcomes. So you can see there are actually 4 different ways that the coins could look, right? A lot of times students think it's 3. Head, head, tail, tail, and 1 of each. But you have to break apart 1 of each and actually spell it out, okay? So the question is, What's the probability that you get tails both times? What's the probability of getting tail, tail? Well, that only occurs once out of the 4 times, which would be 25%. So is it unusual? No, it's not unusual. Happens 25% of the time. But that's how you can kind of create the sample space rather than just sitting down and thinking about it. Now, you could probably just think about it and get this, but what if you flip the coin 4 times? Have fun just thinking about it, because it's going to take forever and you might miss one. So you could just keep branching off. Of course, that's not really all that fun either. But we'll stick with the small one. So a tree diagram is a nice way to organize your thoughts if you think that that would be helpful.